Good evening, kids. Today we're going to review a little topic known as diffusion. So, first we're going to ask a question: what is diffusion? Right? So, we can say that diffusion is actually the movement of individual molecules or particles, if we're talking about gas or liquids, uh, from an area of higher concentration to an area of a lower concentration. Now, what is concentration? It is the amount of a substance in a given area. That is what we call concentration, right? So, what happens that once a diffusion occurs, the concentration which was from higher to lower will become the same for all of the container. It would distribute in that given area. So let's try this in FET simulations. What we actually mean by this, let's experiment with this. So for that we're going to go to the physics simulations. In physics simulations you're going to find diffusion. Once you open that up, you're going to end up on this simulator, right? Now, as of start, we are going to look into just one gas. So there's one blue gas over here, or blue fluid, and then we have a red one, right? So I'm just going to start with the red one. So over here we have 10 particles, right? Now this white, you know, uh, rectangle is actually the area in which this gas is entrapped. Now, as you can see, it is divided into two parts. One with the higher concentration. If I increase the number of particles, as you can see, the number of particles in this area on the left are greater than as compared to the right, and for now we have none on this side. So once I remove the barrier, you will see that these particles which are now concentrated in this area, which is a higher concentration area, will try to move towards an area towards the right which is at lower concentration. So let's remove the divider. Now after removal of divider, as you can see, this gas has started to uh, distribute itself evenly. So you can see now the concentration on both sides is apparently the same, right? This is what we call as diffusion, right? Now this may occur between two different gases, two or more gases, right? So we're going to experiment on that, but first we're going to see what is the effect of mass and what other factors may affect the movement of these particles, right? So let's get back to the question. The second question we should be asking: on what factors does the rate of diffusion depend upon, right? So number one is temperature. So more the temperature, definitely the gas particles will have more internal energy and they will move more freely. Compared to that, the effect of the mass can be put together like greater the mass. Since the particle is going to be bigger, it is going to be harder to move about, right? So we're going to experiment with these two factors in the simulator. Let's get back to it. Let's reset the simulation. Let's set the particles to, let's say, 40, and let me reduce the mass. I'm going to reduce the mass to minimal most. As you can see, the more I reduce the mass, the faster the particles are becoming, right? Now with the minimal mass, they are very fast, right? And the same way, if I remove the divider, you can see that the diffusion is occurring much faster, right? Previously it took some time to distribute itself among the whole of the container. Now it did it very fast. Let's retry again. uh, Put about 50 particles in there and reduce the mass. As you can see, the movement becomes more violent. Now that also we have seen with temperature, right? With lesser mass, less difficulty in movement, so the particles are moving very fast. uh, so if you increase the temperature, which is in kelvins, the more I increase the temperature, the particles become even faster, right? Now even if I increase the mass, you will see that the particles are slowing down, right? And if I reduce the temperature now, you can see the particles are ultimately slow, right? So if I remove the divider, it will take a huge amount of time for these two areas to be at the same concentration level, right? So This is what diffusion of a single gas in a single container which has a divider to create a higher and a lower concentration would look like, right? Now we're going to experiment with two different particles as well, right? Now I hope you understand these 2 points, that how the temperature is affecting and how the increase or reduction in mass affects the rate of diffusion. The greater the mass, the less the diffusion. The lesser the mass, the greater the diffusion. It's an inverse relationship in terms of temperature. We have a direct relationship. The more the temperature, the more the internal energy to move about. Hence, faster diffusion is going to occur, right? I hope these two are clear and we understand what diffusion is. So let's experiment what the simulator has to offer, right? So we're going to reset this. Now we're going to add 30 particles or 40 particles for the blue one, which is a heavier mass. It's a bit slow, and we're going to add equal amount of red particles, except we're going to reduce the mass so that it's a lighter gas, let's say hydrogen. And since it's 4, so we can say this is helium, right? It's 4 AMU, so it should be helium. Over here, since we have 32, let's bring it down to, yeah, 32. Let's call it oxygen molecules, right? These are helium atoms, since atoms are supposed to be single, and let's call these blue ones as molecules, which are for oxygen at 32 AMUs. I'm going to reduce the radius as well. Now you can see these uh, helium particles, since they are very small, so they're very fast as well. Now, I'm not going to touch the temperature for the moment because I want both these gases to be at the same temperature once they start diffusing into each other. So you can see, the net movement. Right now, there is no net movement between these two areas. Uh, we can see that once the divider is gone, and this can also scale in nanometers how the particles are moving about. So I'm not just going to turn up any of these options. You may turn up the stopwatch if you want, but I'm still going to keep it off because I just want to visualize how these mix together. I'm going to remove the divider. Once I do that, as you can see, the particles are mixing together. The red ones are fully diffused while the blue ones are taking their time since they're heavier. As you can see, even though these particles are very small, once they hit these blue particles, they actually alter the path or slow them down or give them more speed, right? So this is what a smaller gas is going to do. This is also kind of an example of Brownian movement, in which your sample particles are moving about in the microscope once they're hit by the liquid molecules, for example water. If you have pollen grain in water, then consider these blue particles as pollen grains, and the red particles as water molecules which are pushing them about. Now I'm going to do the same thing here, and I'm going to increase the number of particles just to signify how Brownian movement should look like in you can say in your microscope, right? So look at this, right? Just watch what is gonna happen to these blue molecules. They won't even get to go anywhere, right? They're just pushed about randomly in random directions. Why? Because these particles are hitting them around. So this is also an example, a very good visualization for Brownian movement, right? Along with diffusion. So this is the topic of diffusion. I hope I was able to clarify some of the confusions you guys have, and I look forward to having some questions from you in the comments. Thank you so much. Bye bye.